and maybe a little bit of tomorrow is going to be kind of like the basic probabilities. And then as we progress through this chapter, we'll get to things. I don't think you've learned permutations or combinations yet. Does that sound familiar? Okay, so those are new counting methods that we can use to do problems that are too big for us to count. So our level of difficulty and probability will definitely increase as we go through the chapter. Really important is that you're doing the practice, because the majority of probability where people struggle is you have to read the problem and come up with a plan. Every problem's different. So you gotta be willing to put yourself in it so you're kind of used to it and coming up with like, okay, this is where I would add, or this is where I would multiply, so that you're feeling well practiced. I gave you a blue packet that has all the notes for chapter 10. And that way, because probability, your problem might be like this whole long scenario, and I don't have time for you to write that down from the board. So we just have the problems that we might get to in the packet. They're available for us. If you don't like the packet, if it's too restricting when you're taking the notes, you can always take notes in your own notebook, and if you need to just like refer to the packet for examples, you can. So that's totally up to you. It's just there for everybody, and that's all our notes for chapter 10. So if you do miss a day of class, I always post my video notes online by the end of the day. So you could watch that video, take the notes in your blue packet, do the homework or assignment, and you'd be caught right back up with us. Okay, let's start talking about basic probability. I'm not sure if you study officially a sample space in your like middle school or elementary math, but basically a sample space is the list of all possible outcomes. Okay, so when you're trying to decide like what's the probability that I would put all your names in a hat and then I would pull your name specifically, our sample space would be all the names that are in this classroom. Okay. So it's a set of all possible outcomes. The first example that we're going to do, and I'll give you some time here in just a moment with your pods, like a minute or two to get some ideas here, is we're going to toss 3 coins. Okay, and we want to list the sample space for the possible outcomes when I flip 3 coins. So just to kind of get our brains thinking, every time you flip 1 coin, what is your sample space? Heads, tails. Okay, but we want to flip 3 at a time. So isn't it possible that one outcome is heads, heads, heads? And so you might have seen this, you might have done this before. You can write it out and you can use like some abbreviations. Okay. So this is going to be my first outcome that's possible, heads, heads, heads. You guys discuss with your group, see if you can get all the other outcomes. What else is possible when you flip 3 coins? Count up how many you have at the end. So we'll see if we got the same number of outcomes.
Heads, tails, heads.
Yeah, because your first coin could be different than your second coin, your third coin, right? First coin being heads.
Heads, tails, tails. No, we haven't gotten to that. Tails, tails.
Okay, let's come together and list some. So you can just kind of one at a time. Somebody shout one out and I'll write it up. Heads, heads, tails. Tail, tail, tail.
I keep changing my answer. I have 9, 8.
Heads, tail, heads. Tail, heads, tail. Tails, tails, heads. Tails, heads, heads, and heads, tails, tails. 8 of them, right? Okay. So this is our sample space, okay? And we have 8 total outcomes. We're not going to get to this method of figuring out how many outcomes are possible until about halfway through the chapter, but I want to talk about it right now because you've probably already learned it. It's called the fundamental counting principle. But another way to make sure that you've got like all the possibilities in the sample space is to think about it like this. If I'm flipping 3 coins, that's basically like 3 separate events, right? Coin 1, coin 2, coin 3. How many ways can you flip coin 1? 2. And how many ways can you flip coin 2? And how many ways can you flip coin 3?
2.
So you multiply all those together, 2 times 2 times 2, or 2 cubed, and you get 8 total outcomes. So by the fact that we listed all 8 of them, we're sure we have a complete sample space. So that's called the fundamental counting principle, probably something that you've seen before, where you just multiply the number of ways something can happen. I won't spend too much time on this next one, but I am going to show you, like, there is an official way to write the sample space, so I'll show it to you for this extra example with 1 die. Suppose you roll 1 die. What are the possible outcomes? 1 through 6, right? Okay. When mathematicians write sample spaces, they use squiggle brackets. They make a bracket and then they list the different outcomes that are possible. Now, right now, I'm not too particular if you use that like actual notation for sample spaces, but if you want to give that a go, you can. If you ever see that in a textbook, that's what we've got. Okay, now I do want to take a little bit of time to talk about rolling 2 dice. Okay, so there's generally, there's different ways that you can find the sample space for rolling 2 dice, like what are the numbers that are going to be on the dice. And one that I want to show you is what I would call a tree diagram. We're going to see this a couple more times in our probability chapter. So in a tree diagram, I could do something like talk about the first die. Okay. And the first die can have the 6 different outcomes that are in my sample space from part A, right? Like I could roll a 1, a 2, a 3, and then I'm going to put a 4 and a 5 and a 6, right? The red indicates my first die. Like those are the possible outcomes, 6 of them. But then I have to roll a second die. I'm going to call that the blue die. Well, if I roll a 1, when I roll the second die, this one could turn out to be 1 through 6, right? So I could be like 1, 2, 3, 4, 5, 6, and that could be with the 1. So that's kind of like the tree diagram. It has the branches. It goes out to all the outcomes for dice number 2. And so really, if I roll a 1 on the first die, there's actually 6 possible outcomes for the 2 dice, right? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And same for 2, right? 1, 2, 3, 4, 5, 6. And I got that nice tree diagram. And I could do that for all the numbers. I'm not going to take the time to do that, but you could certainly if you wanted to. How many outcomes are you going to get total? 36, because you're going to have 6 groups of 6, right? Which makes sense because by that fundamental counting principle I mentioned, take the number of ways you could roll die number 1, 6, times the number of ways you could roll die number 2, 6. There's always 36 outcomes. So rolling 2 dice always has 36 outcomes. If you like tree diagrams, you can use tree diagrams. I'm also going to show you, I'm a big fan when I try to do 2 dice problems. Me personally, I like a method, and I don't always draw these like parts of the chart, but I like to think about it like I have rows and columns with my 2 dice. So I could get a 1 through 6 on one and a 1 through 6 on the other, and then I could just like match up like what's possible. So in this first column, die number 1 is up here is always a 1. So I could get a 1 and a 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And then in this column, I would get a 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. And if you want to go through in your notes someday and you want to fill out all of that, you certainly can. Okay, but that's an easy way to generate what the 36 outcomes are. Okay. What I like about this method is it makes it easier to see, for example, that rolling a 2 and a 3 is different than rolling a 3 and a 2. Just like some groups ask me on the coin problem, is heads, tails different than tails, heads? Yes, because it depends which penny or which die it is, right? But notice also if you were to complete this chart, these values in the diagonal going down, they're your doubles. How many ways can you roll a double on the dice? There's 6, 1 for each of the numbers, right? But like a 1 and a 1, you don't count that one twice because there's only one way to get a 1 on both die. So that sort of sometimes like boggles people's minds, like why I would count 2 and 3 different than 3 and 2, but why I don't count 2 and 2 twice. Okay, the sample space makes that more clear if you need it. Okay, more about probability basics, and you can decide what you want to fill in on the notes, okay, from what I have on this slide. First of all, probability's definition is it's the likelihood that an event would occur. Sometimes people use the word odds to talk about probability, but to be real honest, mathematicians consider odds to be something different. So I like to think about it more as like the likelihood of an event occurring. Make sure you get this new notation down. When we're working in probability, we're going to be using capital letters. And it sort of looks like our old function notation, f of x. So p of a. It's the probability that event A will occur. And you can put anything you want in for A. So like, let's say we have somebody who's expecting a child. So we might wonder, what's the probability that it's a girl? So we can write that in. Or we could have, maybe last night you were wondering, what's the probability we're going to get a cold day? Okay. Sorry to bring that up. Okay. So you can put whatever you want. Or like, what's the probability you flip 3 coins and you get 2 heads? Okay. So you can sort of write it out in that notation so then everybody knows what you're talking about. Okay. This right here is super important. You can also think about it in percents. So the probability of an event A can be between 0% and 100%, but you can't have more than 100, you can't have less than 0. So listen very carefully. If on a quiz or a test, I ask you about probability of an event, you should never accept a negative answer from your calculator. And you should never accept a ratio or a fraction or a decimal that's more than 1. You would be like, there is a problem, right? If you're willing to write down negative probabilities, it makes me question if you've even been listening. So then I don't often give you a lot of partial credit for that one because it just doesn't make sense. I'd feel better about it if you wrote me a note. It's coming out negative. I know it can't be negative. I don't know what's wrong. Right? That would at least like calm my fears that you weren't even here. Okay, so it has to be between 0 and 1. And then I've got that scale on there. I'm sure that you're all pretty comfortable with this. As your probability moves closer to 1, it is more certain that your event will occur. The likelihood is higher. If your probability is 1, there is no other option than your event to occur. If your probability is 0, your event will absolutely not happen. There is no chance. And then in the middle, you're probably familiar with a lot of situations that are 50-50. Okay, tossing the coin, some fair games have to be a 50-50 probability. Okay, next up we're going to chat really quickly about something called a complement. This complement is spelled differently than the kind of compliment I might give you when I say you look nice today. That has an I in it for this first E. Okay, so it's different. This is more like the mathematical complement. You've seen the word complement before with angles, right? What angle is the complement? They have to add up to 90. But in probability, the complement is the probability of something not happening. So it's like the probability of the opposite. Make sure you get the notation for the complement. Okay, it looks like A with an apostrophe. So you might read that as A prime. But I just read it as not A in probability. Or you can say the complement of A. And then sometimes, just as an FYI, some textbooks or some people will use a squiggle for a not. So they could say not A right there. Or for like our example where we were doing the probability of a cold day, the complement of a probability of a cold day is the probability of school. Right? You could say not a cold day, but you could also just say like going to school. It would be its complement. When you want to calculate a complement, it should be very easy. And sometimes it's harder to calculate the original probability than it is to calculate the complement. So you might use the complement and then just subtract from 1 or 100%. If the probability of snow today is 30%, what's the probability of no snow? 70%, right? They have to add up to 100. Okay, and then before we get into our actual experiment here with theoretical and experimental probability, just really quickly, I want to make sure you're comfortable with my methods of calculating probability, which I think you guys already know how to calculate probability. Today is very basic. Okay. But I do want to highlight here 2 words that I'm going to use all the time. When you're asking for help on a problem and the problem is asking about like what is the probability, I'm going to be reminding you that the probability, how do you calculate probability? It's a ratio of favorable to total outcomes. So I use the words favorable and total. Favorable is like what you're looking for. So if we're doing the names in a hat example, your favorable event is your name being pulled from the hat. Coals have a better chance of being picked. There's more than one. And then there are 3 types of probability that all essentially you're doing favorable over total. Theoretical, experimental, and geometric. So just really quickly, and we're going to see this in the, we're going to roll some dice here in just a moment so we can see it play out. The difference between theoretical and experimental is theoretical is what should happen in theory. Based on the sample space, what are the total outcomes that are possible? What are the number of favorable outcomes in that sample space? This is what should happen. But of course we know that's not always what actually happens. So what actually happens is experimental. Okay, theoretical is what should happen. The math tells us so. experimental is what actually did happen. Whether you're collecting the data by running an experiment or you're gathering data from something that took place in history, okay? Someone ran the data and this is what actually happened. So that's the experimental probability. And then I do have a brief expansion on geometric probabilities here. I know there's not a spot for this on the closed notes, so if you wish to include it somewhere, you can. So geometric probabilities are going to be probabilities where, like, most likely you're comparing, for me, areas. I mean, you could do probabilities of lengths, but most of the times it's going to be areas. So it's talking about like a shaded region over a total area or a non-shaded region over the total area. These three formulas that are on the board, you are required to know. I don't need to tell you the formula for area of a rectangle, triangle, or circle on a quiz or a test. You already know them. Okay, so that's like just a whole bunch of information that I wanted to, even though we like really already know it, I need to say it. Because I don't want any negative probability answers. I don't want any probability that's more than 100%. Okay, don't give it to me. Okay. We're going to start with this little activity where we get to see the theoretical versus experimental probabilities play out. So at the bottom of the page, you've got a little chart, and it's kind of separated it out into different shaded regions. So we're going to do line 1 and 2 together. Then you'll do line 3 and 4 with a partner in your pod. And then we're going to do lines 5 and 6 as a whole. Okay. So for line 1 and 2, we can actually do this together. We're going to think about rolling a 6-sided die. And then notice these are our possible outcomes, right, in the sample space, 1 through 6. Okay. On the 6-sided die, how many favorable outcomes are there for rolling a 1? 1, because there's one side that is a 1. How many for rolling a 2? Also 1, and same for all, right? One side of the die on the standard 6-sided die is always one number. How many total outcomes are possible theoretically on the die? 6. So we would all agree that each of these has a basic probability favorable over total of 1/6, yes? In probability, when all the outcomes in a sample space have the same probability of occurring, we call that uniform. And what I'm going to do is I'm going to real quick change this. This is like point, I think, 167 for all of them. Because what I'm going to have you guys do is once I give you and your partner a die, you're going to roll the die 10 times. So you're going to perform an experiment. And you're going to tally up in line 3 how many times you rolled each of the numbers. So like one of you can roll and one of you can tally, or you can work together however you want to get it done. So your total outcomes in line 4, you're going to change that to a 10. It's not going to be out of 6 anymore because you're going to complete 10 experiments. And then you guys are going to calculate the probabilities. You know, if you rolled a 1 3 times, then your probability of rolling a 1 experimentally is going to be 3/10 or 0.3. So you'll do that and then change them all to decimals, okay? So that we can compare them to 0.167, see how close they are. Okay. So when you get your die, I just need you to roll 10 times. No redos. It is what it is. It landed, right? So we can't like get the numbers we want. Just roll 10 times, record it, and split up into 2 pairs for me. So we got data. Nicole, will you come roll with someone over here so we get an extra set of data? And then Matthew, will you come roll over here with someone so we get an extra set of data? The more data we have, the better. It's your partner.
It's your shoulder pod. Actually,
You guys have pods, but I used to have rows and shoulder
We're
buddies.
not shoulder buddies.
You're all the
Technically, I'm not. Shoulder.
We're shoulder buddies. They
But
don't
then,
have shoulder buddies. Sorry, we're just kicking you out. You guys don't. You don't get to participate.
Okay, we're all done rolling, so make your calculations and divide by 10 in line 4. Okay, so change it into a decimal. It should be pretty easy. Did I get all my dice back? I have one more out there.
What's one?
Who did I forget?
Point 1, 10. Point. Oh, that's one.
Okay, you're probably noticing some big discrepancies between the uniform probability that should happen, 16, 17% for each one, and what actually happened in your experiment. Did anybody have any that they rolled zeros? Okay, almost everybody's raising their hand. Did anybody have one where they rolled, like, they thought a lot of the same number?
6.
You rolled a
4
4
6s.
6s. Anybody rolled more than 4 5s? Okay, so those things, like, out of 10, that's not really what should happen, right? You're starting to question my dice. Okay, so now what we're going to do is we're going to pull together our data from the class to see what happens if we have just like more trials. Okay, so what I need you to do is pick one person from your group, your partner, that's going to report to me, and you need to be like paying attention and ready to answer. I'm going to point to you guys, and then you're going to tell me your number for roll 1, and I'm going to add them up, and the rest of you are going to be checking my adding, because it gets hard for me. Okay. You rolled a 1 how many times?
1.
1, 2, 5, 6, 8, 11, 15, 16, 16, 19, 20, 22. So we all write 22 down. This is line 5, 22. How many times did you roll a 2? This group right here.
1.
1,
1.
2, 3, 3, 5, 5, 6, 7, 9, 9, 11, 13. How many times you roll 3?
2.
2,
2.
4, 6,
2.
8,
2.
10,
0.
10,
0.
10, 11, 14, 14, 16. How many times you roll 4?
2.
2,
1.
3, 5,
0.
5,
2.
7,
3.
10,
2.
12, 13,
3.
16, 17,
0.
17,
1.
18. Okay, how many times you roll 5?
0.
0,
2.
2, 2, 4, 5, 5, 7, 9, 11, 11,
4.
15,
1.
16. Okay, and the last one, 6.
4.
4,
3.
7, 9, 14, 15, 19, 20, 25, 27, 30, 33, 35. Whoa! I don't know if that's ever happened in the 30s there. Okay, now I counted that I had 12 partner pairs. So you each rolled 10 times, right? So that would actually be 120 trials that we had. So I'm going to grab my calculator and I'm going to do the probability for these. And then I'll put them up on the board in decimals. Because when they don't have the same denominator, it's hard to compare. the decimal values. So this one is like 0.183. This one is 0.108. This one is 0.133. This is 0.15. This one, of course, is 0.133. And then I really can't believe this is 0.292. Maybe there is something wrong with my dice. 0.292 was that last one. I know it's hard to read. You could always go back and do it if you wanted. But like overall, compare this line 6 to line 4. Well, we still have not uniform probability. Are you seeing less discrepancies? Like the probabilities are sort of like coming in towards that uniform probability. What would you expect to happen if we rolled the dice 1,000 times?
Yeah, we should do it, honestly.
The difference would get smaller and smaller, and it would be more and more like the uniform. Now, will it exactly be the uniform?
No.
No, maybe not, right? There's still a chance that the 6 is rolling more, or just like for whatever random reason, we get more 5s. So it's possible, but we should see that the more times you complete an experiment, the better your data is towards your theoretical probability. If you only flip a coin 3 times, it's probably not coming out to be 50-50. In fact, the best you can get is 67-33, right? So you have to consider that when you're thinking about an experiment and if it really truly models your theoretical probability. Okay, so if you flip over the page, it's got that question, the think, ink, pair, share at the top. And basically, it's asking that question that we just talked about. Like, what do you expect to happen generally as you increase the number of trials? What happens to your experimental probability? It gets closer to the theoretical probability, right? There's the link. If you complete an experiment more often, if you increase your number of trials, your probability, your experimental probability should get closer and closer to your theoretical probability. Now, if it's way off after 1,000 trials, we could assume we've made an error in calculation. And that's something next year, if you're taking the honors pre-calculus class, you do in first semester a game project. You create your own game. You figure its probabilities. You learn about something called mathematical expectation to figure out how much you should be paying out to players when you play the game, and then you run the games to see if they actually came out to be the same. And if they don't, then you go back and you look at your work and figure out if your theoretical was bad or if you played your game incorrectly. So that's an interesting thing that we can do. Let's see. I think, let's talk about example 1. This is a good one, and I'm not too worried if we don't get through it. Like, we're not getting through all the examples, but I'm not too worried about it because it's like basic probability is your homework tonight. You just need to read the problems and try them so we can talk about it tomorrow. But this one's a good one. A student taking a quiz randomly guesses the answers to 4 true-false questions. Been there. What is the probability of the student guessing exactly 2 correct answers? So I'm going to write it out in probability notation. I'm going to say the probability of exactly 2 correct. And remember, probability is favorable over total. Okay, so let's tackle the total. When you're answering 4 true-false questions, how many total ways are there to answer? 2 for the first problem, 2 for the second, 2 for the third, 2 for the fourth. What do we do with all those 2's? Multiply them together. Your total is 2 to the 4th, or I hear some people saying 16. So that's the number of ways for you to answer. And then we need you to answer and get exactly 2 correct. So think about if you were answering 4 questions, I'm maybe going to create my own little sample space of 2 correct. I do this for the dice problems too. Like, couldn't I do, I'm going to do right, R for right and W for wrong. Couldn't I do right, right, wrong, wrong? Or wrong, right, right, wrong? Or wrong, wrong, right, right? There's 3 ways for me to answer 2 right. Can you think of other ways I could answer 2 rights? Right, wrong, right, wrong. Sort of like that 80s song. Wrong, right, wrong, right. Right, wrong, wrong, right. I think we got them. So there's 1, 2, 3, 4, 5, 6. And I would stop and think about the reasonableness of my answer. 6 over 16 is less than 1, but more than 0, so that makes sense. I feel good. So like you might do this where you like list out what things are in your sample space that actually fulfill the probability you're trying to find. Okay? So your homework assignments, that's on the gold sheet. It's at the bottom of the blue sheet. Please try reading those problems and answering questions so that you know what kinds of things you are confused about tomorrow when you check your answers. And it's 12:30.